Welcome back, class. Good to be with you. This is going to be out of Whitlock and Schluter Chapter 9. We're going to focus on odds ratios. Now, the key piece of background that we need is we're in the same scenario as usual. We have some random variable coming from a population. Okay, this could be a random variable called x. There may be two random variables, y. What's distinct about this chapter is these random variables are categorical, okay? Meaning that the possible values they could take on are categories. For example, hair color, for example, height, for example, not height, gender, male, female. Okay, so we're going to often be interested in things like estimating the proportion, which will be the number of successes out of the total number in the sample. Okay, so when I take out my little sample here, then I'm counting the number with whatever trait, and then I divide it by n. Now, briefly, let's look at these basic definitions. There's 5 of them, and I want to assert to you that the first 4 are mathematically identical: percentage, proportion, probability, and risk. Okay? The only one that's different is odds. How so? Percent with trait is just the number with the trait divided by total times 100%. Whereas the proportion, we drop the percent. Probability, it's the same form as proportion, as is risk. So what is odds then? Odds is number with to the number without, as opposed to the total. Let me clarify with an example. Okay, 1 in 4 sexually active teens contract STDs each year, and that's not standard deviations. Okay, so percent with trait is going to be 1 divided by 4, and then of course we can write that as 0.25, and we put this little symbol on the back and call it percent, so 25%. Proportion, of course, is just going to be 0.25. You could also have a fractional form, 1/4. Probability, same thing. Risk, same thing. Now, what's different is the connotation that these have and the context within which they're used. So, if you've got this population of sexually active teens, and I'm just going to cut this pie into 4/4, then the percent, we're talking about the whole population, and we say this percent of them have the trait. Proportion, same thing, but we just use this decimal form language. Now, probability of having is slightly different. We're thinking about an individual, okay, and it's just this green dot here. Well, if that green dot is somewhere in the population, what's the probability that it's in this group, the contractors? Okay, and then the risk, that spins a connotation towards you or towards this hypothetical green dot. Well, what's the risk that you or this green dot lands in the contracted group? Okay, now by contrast, odds looks like this. Odds of having the trait are going to be 1, and we can write colon 3, 1 to 3, or you could put it in a fraction, or you could just put it into a decimal form, although I'd like to note that the decimal form is just 0.33 to 1. Okay, 1 has the trait to these other 3 who do not. That's how the odds look. Okay, so let's get into the odds ratio where things start to get more interesting. Now, start off with an example here from Whitlock and Schluter on page 210. In this example, we have 2 groups. we've got a group of women who were given an aspirin every other day and a placebo every other day. They were tracked for 10 years, and it was recorded whether or not they had cancer. Okay, so I've got a cancer group and a no cancer group. Now, if you look at the data by eyeball, the proportions in each group are virtually the same. But what does that look like mathematically? How do we check for that? That's what we're going after in this part here. So, odds ratio. Okay, whenever we get these two-way tables with categorical variables, we like to put the rows as the explanatory variable x, the columns as the response variable y. Okay, so the odds of A to B, as I said, in a general setting, is just going to be the part to the other part. So A to B. You could write that A over B. Now, technically, we can go ahead and put it like this. If you let P be the proportion in group 1 of the successes, that's A over A plus B, and we let 1 minus P be the proportion of fails, B over A plus B, then odds in group 1 is P over 1 minus P. It's the proportion of successes over the proportion of failures. Okay? And if you write that out, you're going to get A over A plus B all over B over A plus B. These are in parentheses, of course. And these A plus B's in the denominators cancel, and I get that A over B. Okay. Now, that's simply the odds of success in group 1. What is the odds ratio? Okay. Well, the odds ratio is a comparison of the odds of success in two groups. So it's odds in group 1 to odds in group 2. So we write it like that. We have A over B all over, looking up here, C to D, that's success to fail. So C over D. That's the way to remember it. Mathematically, you can go ahead and do the cross multiplication. We get AD over BC. And that's another form of the odds ratio. Now, meaning. Okay, meaning. I've got a little write-up here. And if we call the odds ratio OR, as we will do, then if the odds ratio equals, some different possibilities here, if it equals 1, then that's going to be the same in all the groups. On the other hand, if the odds ratio is greater than 1, then we're going to have odds of 1 are greater than the odds of 2. And if the odds ratio is less than 1, then the odds in group 1 is less than the odds in group 2. Okay, let's see what that means in our specific example. Okay, so to compute it in our example, let's go ahead and write that odds ratio out. Let me put it here. Okay, just grabbing the numbers, I'm going to have 1, 4, 3, 8 over 18496 all over 1427 all over 18515, which, when we run that calculation, it's going to be 0.992. Wow. Okay, so that's the odds of getting cancer or not cancer in group 1 versus group 2. It is so near to 1, as we observed by eyeball, to be virtually the same. and that's what we were expecting. Now, clearly it's slightly less, but not in a statistically significant sense. Okay, last thing, confidence intervals. We've already covered confidence intervals in Chapter 4. So here's the statement of the confidence interval for odds ratios. And now, let me first give the background here that comes from Chapter 10. So I'm just going to state it from the standpoint of that language. If you've not covered Chapter 10 yet, then this will make more sense if you come back to it after doing Chapter 10. So the assumption is that under modest sample size conditions, if we take the natural log of the odds ratio, then it is approximately normally distributed. That is the bell-shaped curve. I'm going to just let natural log of odds ratio, let's just call this script O for our purposes here. Okay, I'm going to put a hat on for the estimator, and I will not put a hat on for the population parameter. Okay, so the true unknown odds ratio is in the center of the curve, and then the sample odds ratio, whatever we get from a sample, if you were to take many of them, then it would fill out this bell-shaped curve. And it has a certain standard error given by this ugly looking formula. So what we do then is, to make our confidence interval, we're going to put the estimator in the middle, as we mentioned in Chapter 4, and we're going to do the estimator plus the margin of error, and we'll do the estimator minus the margin of error. Okay, I'm fighting this a little bit here. Minus margin of error. And as we said before, the margin of error is that z-score, which for the 95% confidence interval, we use a 1.96 times the standard error. And that will do it. Okay, so let's go ahead and calculate the confidence interval for log odds in this particular problem. Okay, so the statistic that we want is going to be this script O hat, which is natural log of, we had 0.992. We already calculated that number. That is minus 0.00803. Okay, standard error. This is an ugly calculation, so let's write it out. For the two-way table, we have 1 over A, which is 1438, plus 1 over B, that's 1 over 18496, plus 1 over C, 1427, plus 1 over D, 18515. So take the square root of all that. This is when you'll want to check on your calculator that you're doing the operations correctly. 0.03878. Okay, now using that then, let's go ahead and calculate our margin of error for the 95% confidence interval. We're going to do 1.96 times standard error minus 0.00803. Okay. Excuse me. 0.03. Say 0.039, which gives us approximately 0.076. So the confidence interval, sketching the diagram, is going to be centered at minus 0.008, and we're going to add and subtract this margin of error, which is going to give us minus 0.084 to positive 0.068. Now, that is not the final result that we're looking for. Notice this is on the scale of the odds ratio, log odds ratio, okay, not of interest to us. So we need to convert, since we took a natural log of odds ratio, to undo the natural log, we exponentiate. Take e to that power, and that will give us our original odds ratio. So doing that, we get e to the minus 0.084, which will be e to the natural log of our estimate, e 0.068. And doing that arithmetic gives us 0.92 to 1.07. Now, from the standpoint of the confidence interval, we're 95% confident that the true unknown parameter is contained in that interval, 0.92 to 1.07. I'd like to go ahead and put that up on my curve because that's truly the interval of interest there. Now, since 1 is contained in that interval at the 95% confidence level, it appears that the unknown parameter is somewhere near 1, meaning that the odds of getting cancer is the same for the cancer group, or excuse me, the aspirin group and the placebo group, which means that taking the aspirin every other day does not appear to have an effect on the cancer.